Hello students, today our topic is AC voltage applied to LCR circuit. Okay, means LC and R, they are connected in series, inductor, capacitor and resistor. In our previous video we have already studied about individually, means when AC voltage is applied to resistor, when there is only inductor and when there is only a capacitor. So now all these three components are connected in series. So if I draw, let's take this AC voltage, capacitor, inductor and resistor. L, C, R. All three are connected in series. Okay. Now see the voltage, AC voltage is applied. So I will write down Vm sin omega t. Okay, so now there will be voltage drop across capacitor, inductor and resistor. So if I apply Kirchhoff's law, okay, if I apply Kirchhoff's second loop rule, then what I will get? Vm sin omega capacitor. What is the voltage drop at capacitor? Q by C. At inductor, L di by dt. And at resistor, V equal to IR. Okay, so I can write it down as L di by dt. This is the voltage drop at inductor plus the voltage at resistor, that is IR, and the voltage at capacitor, that will be Q by C. This will be equal to Vm sin omega t. So this is the equation. Okay, this is the differential equation of a series LCR circuit, where L di by dt plus IR plus Q by C, that is equal to Vm sin omega t. Okay, so what is this? Differential equation of LCR series connection. Here, now let's draw the phasor diagram for it. Okay, let's draw the phasor diagram. Okay, we have already studied that for current and voltage. If I take capacitor, then voltage leads. If I take inductor, then current leads. Clear? And in resistor, current and voltage both are in same phase. Okay, so now let's draw the phasor. Phasor diagram. Okay, first let's draw the current vector. If I draw the current vector as I, let this be the current vector I. Okay, now if I take resistor, when I take resistor, then the current and voltage both are in same phase. Clear? So the voltage vector will be this one. Let's take this as VR. Okay, we take this angle as omega t. Means at any time, if I is the phasor vector, okay, I is the phasor of current, then this will be the phasor of voltage across resistor VR. Okay, now if I take inductor, now what leads in inductor and what lags behind? In inductor, voltage leads by a phase of pi by 2, or current lags behind by a phase of pi by 2. So voltage will be ahead by a phase of pi by 2. So the phasor for voltage of the across inductor, let's say this will be the phasor for voltage as for inductor. This angle this will be equal to pi by 2. Clear? That will be pi by 2. Now for capacitor. Now we know that for capacitor, voltage lags behind by pi by 2 phase than current, or you can say current leads by a phase of pi by 2. So if I want to draw for capacitor, voltage across capacitor, its phase will be this way. This will be VC. Okay, and this angle will be pi by 2. So omega d minus pi by 2 for capacitor and omega d plus pi by 2 for inductor. Clear? For voltage, because it is lagging behind by current in capacitor. Clear? So this was about the phasor diagram. Okay, so just note down when we will move forward. Okay, so now in this phasor diagram, I represent the phasor for current VR, that is parallel to I. Okay, inductor, voltage for inductor leads by pi by 2 with respect to R. And for capacitor, lags behind by pi by 2. Okay. Now, if you want to find out the maximum value, means the amplitude, Vm, maximum voltage for across inductor, maximum voltage across resistor, maximum voltage across capacitor. That means the amplitude. Okay, amplitude across resistor means Vrm, M for maximum. That is equal to V equal to IR, so it will be equal to IR. Okay, this will be the length. Okay, amplitude, or I will say length of phasor. Okay, so V will be equal to IR. Across inductor. Okay, across inductor it will be I into X L. Okay, clear? And across that is inductive reactance, and V across capacitor, that will be equal to I into XC. Okay, where XL that is omega L and XC that is 1 upon omega C. There are the component equivalent to resistance in the resistor. So these are the maximum values. Okay, these are the maximum values. Okay, it's not capital. Okay, R for resistor, L for inductor, C for capacitor, and represent its maximum value, the amplitude. Now the resultant voltage. See, inductor, capacitor and resistor, all three are connected in series. So the resultant voltage will be equal to VR plus VC plus VL. Okay. Now say, I am representing it once again. If I draw the current vector, okay, towards the positive x-axis, then what will be the voltage across resistor in the same direction? This is VR, voltage across inductor leads by pi by 2. This is Vn, you can see here it leads by pi by 2, but here I have taken the current on x-axis, and voltage across capacitor lags by pi by 2. VC. So now you can see that VL and VC both are on the same axis. So the resultant I can draw it as this one. This for resistor and this VC minus VL. Okay? So this will be VC minus VL. Got it? Because VC I subtracted VS from there in opposite direction. Okay? So the resultant voltage vector, this will be the resultant voltage vector. Okay? And this will be the phase difference phi. The phase difference between the current and voltage. Okay? So now, if I see this, I can represent the right angle angle. Right? What is this? VC minus VL. What is this? VR. So the hypotenuse, that is the resultant V. Okay? So V will be equal to, I can write it down, hypotenuse, that is V square, that will be equal to VR square plus VC minus VL square. Okay, now I already know the formula value. If I take maximum voltage, okay, then this will be equal to IR square. Okay, when I take maximum magnitude, then VM square, that will be equal to IR square plus VC, that is IXC minus VL, that is IXL whole square. Okay, and V, that will be equal to IM, right? V, that will be equal to IM. Here it will be I square also, because it's VR square. So I square, sorry, if I take I square common here, okay, I square common, let's take maximum, then Im square will be common, R square plus XC minus XL whole square. Here is Im x square, so I have taken I square common. So this is Vm. So Im will be, Im square will be equal to Vm square upon R square plus Xc minus XL square, or Vm upon under root of R square plus Xc minus XL square. This is called Z. Z is the impedance. See, for resistor we are taking resistance. Inductor we are taking inductive reactance. Capacitor we are taking capacitive reactance. So overall, for all three components we will take impedance. Z is called impedance. Okay, Z is called impedance. The formula for Z, I can write it down. Z is equal to under root of R square plus Xc minus XL whole square. I can also write instead of Xc 1 by omega c minus omega L whole square. Okay, clear? So first note down delay, then we move forward. Now, if I represent it on this side, so when there is a current vector on x-axis, the voltage vector, resultant voltage vector will be this, and this is the phase difference between current and voltage. Clear? So if I project it here, this is voltage across resistor in the same direction as that of current, and if I project here, this is voltage across capacitor and inductor. So this will be VC minus VL. Okay? So now if I want to find out the phase difference between the current and the voltage, then tan phi, this will be equal to VR upon VC minus VL. Sorry, it will be VC minus VL upon VR. Opposite upon adjacent. So this will be VC minus VL upon VR. Now voltage across capacitor, that is IXC. Voltage across inductor, that is IXL, and across resistor, that is IR. So when I take I common in the numerator, it will get cancelled. So tan phi, this will be equal to XC minus XL upon R, or I can write phi equal to tan inverse XC minus XL upon R. Clear? Okay. Now say if XC, okay, if XC is greater than XL, if XC is greater than XL, in this situation we are taking DC greater. Okay, in that case current leads and voltage lags. Okay, in this situation current leads and voltage lags by phase difference phi. And if XL is greater than XC, if XL is greater than XC, in that case current lags and voltage leads. Okay, if XC is greater, if X is greater than, current leads and voltage lags, and if XL is greater, then current lags, because here the dominant part will be inductor, in this case the dominant part will be capacitor. Clear? Okay. Now to draw a graph of current and voltage when LCR is connected in series. Okay. So if I draw the voltage vector by yellow color, okay, this is for the voltage vector, and for current vector it can be like this. Means this is becoming maximum at this place and this is at this place. This difference is the phase difference phi. Clear? So this is the graph of V and R versus omega t. Clear? So this was about AC voltage applied to series LCR circuit. So note down the last part.